for this question, you have two vectors. Let's say 1, -1, 2. Another vector here, -3, 1, 1. And what you have is a plane that's perpendicular to both of these vectors. In other words, see, planes are infinite, right? The plane that we're talking about is an infinite plane. And that infinite plane, if you drew the vector that's starting from the origin, it's not going to meet. They're all like they're going parallel. They're never meeting in any direction. Okay, that's what I'm saying. Or another way to say it would be that if you move these vectors so that the initial point is here, then both of these vectors will be lying inside the plane completely. That's what I'm saying. Is that okay? So given that, and there's also another point in this plane, let's say there's some point here that's 1, 0, 2. So given those two information, the goal is to find the equation of the plane. So let's start with the equation of the plane, which is a times x minus x1 plus b times y minus y1 plus c times z minus z1 equal to 0. That's the equation of the plane. Where x1, y1, z1 is a point on the plane, and that's already given to us, so we can think of x1, y1, z1 as this one. And what's the meaning of ABC? Yeah?
It's the vector that's parallel to?
No.
It's the normal vector?
It's the normal vector, right? ABC is the normal vector, which is the perpendicular vector. That's what we want. So now what we need is, from these two vectors that are parallel to the plane, we have to figure out a third vector that's perpendicular to both of these vectors. No, not that. What did you say? Cross product. Yes, that's correct. Yeah. So we can make use of the cross product because cross product does exactly that. If you're given two vectors, the cross product of the two vectors gives you a third vector that's perpendicular to the given two vectors, right? Yeah. Given by the right-hand rule. So that's what we're going to choose as A, B, C. Notice that ABC is not unique because there's this vector that's perpendicular, but there's another, the opposite direction is also perpendicular to the surface as well, right? And you can have like arbitrary length, so you can multiply by 2 or divide by 2. Yeah, so there's many different possibilities for ABC, but among them, we'll just use the cross product of the two vectors. Okay? So that's what we're going to compute. We're going to compute I, J, K, and then 1, -1, 2, and -3, 1, 1, like that. Okay, and then you have to do row expansion. So remember the checkerboard of signs is plus, minus, plus. So apply the checkerboard of signs. So it's plus I times, you delete the column and the row containing this element, which will give you this as your minor matrix. Minor matrix becomes this. And then applying the minus, the checkerboard of signs says minus J is minus J. And then deleting the row and the column, the minor matrix is 1, 2, -3, and 1. 1, 2, -3, and 1. Plus K. And then deleting the row and the column is 1, -1, -3, 1. 1, -1, -3, 1. Which is going to be equal to I. And then you have AD minus BC, so -1 minus 2, that's -3. So we're doing AD minus BC. AD minus BC. Negative 1 times 1 is negative 1. 2 times 1 is 2. So if you do negative 1 minus 2, you get negative 3. Minus J. 1 times 1 minus negative 6, so that's going to be positive 7. Plus K. And it's 1 and then minus 3, so negative 2. Which gives you negative 3, negative 7, negative 2 as your vector. That's going to be a vector that's perpendicular to both of these vectors, right? And now that I have ABC, this is going to be our ABC, and we also have x1, y1, z1, we can write the answer. Answer would be negative 3 times x minus 1 minus 7 y minus 0 and then minus 2 z minus 2 equal to 0. And then yeah, you should really try to write down your answer in terms of the standard form, which is something x plus something y plus something z equals some constant on the right side. But I also don't like the fact that everything's minus, so let's multiply by minus first. Okay, so all the minuses now became pluses because I multiply by a negative 1. And then if I expand this out, you get 3x minus 3 plus 7y plus 2z minus 4 equals 0, so that you get 3x plus 7y plus 2z equals to positive 7. Yes?
Why do we use a perpendicular vector when we're trying to find the parallel plane?
Because ABC is the vector normal to this plane.
Oh, so it has to be 90 degrees to the plane.
Yeah. So if you want to write down the equation of the plane, you need a perpendicular vector. A comma B comma C is a perpendicular vector. All we are given are the two parallel vectors. How do you get the perpendicular vector from the parallel vectors? You take the cross product.
Okay.
That's what I did. Okay, so that's solution 1. Now, let me give you another way of solving this, which is important for another reason, okay? So here's a second approach. The second approach is to just say x comma y comma z is another point on the plane. Okay? Then you get another parallel vector by picking a vector that starts from 1, 0, 2 and ends at x, y, z. Agreed? Yeah. What is that vector? To get a vector between 2 points, you have to do terminal minus initial. Since the terminal point is x, y, z, and the initial point is 1, 0, 2, you get x minus 1, comma, y minus 0, comma, z minus 2. Okay, so that vector that we get here is this vector. Okay? And that's another parallel vector. Okay? Now, when you have 3 vectors that's all lying in one single plane, in that case, you say the 3 vectors are coplanar. Okay, so the idea that I'm going to use is that idea, these 3 vectors, 1, negative 1, 2, negative 3, 1, 1, and this vector, x minus 1, y, z minus 2, are coplanar. Sort of like saying that you have 3 points on the line, then you say it's collinear. Here, you have 3 vectors lying in a plane, you say they are coplanar. Okay, so what? Well, it's been a while, but we learned something called a triple scalar product, right? So let's just review the triple scalar product. Triple scalar product, which was that if you had 3 vectors u, v, and w, then either u dot v cross w, or it could be u cross v dot w. Anyways, if you do that, that gives you, that's same as just writing these vectors like that, right? You just write these vectors as rows, and then you just take the determinant of that. And then I also explained the geometric meaning of it. What's the geometric meaning of that determinant? If you have 3 vectors in space, and if you take the determinant of those 3 vectors in that form, what do you get?
Is it volume?
It's a volume of some object. What?
Power pipe then?
Power. Very good. Yeah. Amazing. All right. So I actually didn't expect anyone to remember that, but that's pretty good. Okay. So you have 3 vectors, and that gives you something called a parallel pipe, right? You get this parallel pipe, and the volume of that parallel pipe is that one, okay? Now here comes the crucial question. If you have 3 vectors that are coplanar, what would the determinants give us? If the u, v, w lie in a plane, what would be the determinant value? If all 3 vectors lie on a single plane, what would be the volume of the parallel pipe?
0.
0. You have to be able to imagine it. Like if your 3 vectors all lie on a single plane, nothing is popping out. So the parallel pipe also lies on the plane. All the parallelogram that you can draw out from here, all of these lie on this plane, right?
It's like this.
So it's totally flat box. It's like taking a box and you just squash it down so that it's inside the plane, right? What's the volume of that parallel pipe? 0, right? So it's 0, therefore, we can do that. So what I'm trying to say is an important point that U, V, W are coplanar. That means U dot V cross W, this determinant is equal to 0, okay? That's the thing that we're using. So we can say that 1, -1, 2, -3, 1, 1, x minus 1, y, z minus 2 has to be 0. I wrote these things too close together, so this is one element, that's one element, that's one element. Okay. All right, so now I have to calculate this, and there's several ways to do it, but I like to, let me expand over here, because these are the ones that are the most complicated, and I think this should be the easiest, okay? But first remember the checkerboard of signs. It's plus here, minus, minus, plus, minus, no, that's plus, that's minus, plus, minus, plus. So if you expand here, the checkerboard of signs is plus and then minus and plus. So we apply that. X minus 1. Delete the column and the row containing x minus 1. That gives you -1, 2, 1, 1. And then you put minus y because of the checkerboard of signs. and then you delete the column and the row, you get 1, 2, -3, 1. Okay? And then plus z minus 2, and then you have 1, -1, -3, 1. And what do you know? You get the same exact formula that we did for solution 1, which is that you end up with -3 x minus 1, -7 y, and then negative, this will be negative. -4. Did we get -4? Maybe I missed something. 1, -1, 2, -3, 1. Okay. 1, 2, -3, 1. 1, -1. Okay, that's right. What was my previous answer?
Wouldn't that just be 1 minus +3, which would be -2?
This one?
No. Z.
This one?
Z. Oh wait, you're not doing Z?
This one is 1 times 1 minus
+3.
3. Oh, so it's -2. Yeah.
Yeah.
Okay. Was that the correct answer?
Yes.
Okay, good. Okay, thank you. All right, and that has to equal to 0, right? That was our point, right? So once you get this, you see that the final answer is exactly the same as the answer to the previous one. Now, while I took some time to explain what's going on, if you think about it, really the only thing that we had to write was really just this, from here to there. Do you agree? Like all the other ones were somehow just trying to explain what's going on. So when it comes to a question where you're given two parallel vectors and you're given a third point and you have to figure out the equation of the plane, this is actually much faster. Okay? And another nice thing about this is that you don't really have to memorize the formula for the plane because it's just there.
Why did we decide that they're coplanar?
Huh?
How did we decide that those two vectors were coplanar?
3 vectors are coplanar.
Yeah, but how did we decide that those specifically?
So we were already given two vectors that were embedded inside the plane, right?
Yeah.
Yeah, so 2 vectors are already inside the plane, and we had 1, 0, 2, and we decided to call this other point as x, y, z. And therefore, because those 2 points are both inside the plane, if you get this vector, that's also embedded in this plane. So all 3 lie on a single plane, so that's coplanar.
Alright.
Yeah.
So it's not like, because earlier you had it drawn like as if it was almost like the 2 vectors that are at the same spot, they were lower. So like
Yeah, because vectors can be, like, they can be put in different places, right?
Yeah.
So what I was saying is that, well, if you put the vectors so that this is the origin, then it makes sense to just say they're parallel, right? But what it means is that if you bring this point up here so that this initial point lies inside the plane, then this will be fully embedded. Yeah, it won't be sticking out. That's what I'm saying.
Alright.
So none of these 3 vectors stick out from the plane, and that's another way to say that it's coplanar. Okay? Alright.